All right, I will begin. Let me begin with a word of prayer. Dear Heavenly Father, we thank you for this day. Again, Lord, I thank you for the student. Help us to use this time wisely and just to learn more about abstract algebra. You never pray, Lord Jesus. Amen. Remind me where we got to last time. Was it lecture 12?
I think you already went through.
I went through 12 already. Okay. And so I will embark into 13. Okay, so let's see here. Here we were supposed to find, basically go through the calculation to come to an understanding of what the subgroup of the permutations of 8 elements are isomorphic to the quaternion 8 group. And so the idea basically is to track through Cayley's theorem and to see what motion each left multiplication produces. So it's not a terribly exciting calculation, but minus 1 goes from identity to minus 1 and back again, and likewise this and this and this. So that gives you this product of two cycles. Then Li was a little bit, I made a mistake here originally. And I was like, it was so weird. It was like, why is this one different than that one? I, J, and K are like symmetrical. Whatever I prove about I should be kind of the same for J and K, because there's like some sort of, like rotational IJK replacement symmetry here in this problem, so to speak. And although that sort of symmetry I haven't defined carefully in this class, but you know what it is nonetheless. And but as you can see, J goes to, if I take 1, then multiply by I, go to I, then minus 1, then minus I, and then back again. On the other hand, J goes to K, and then I times K is minus J, and then I times J is K, but I got a minus, so I get minus K. And then when I multiply I times K, I get minus a minus J, which brings me back again. And then according to our enumeration, that's 1, 3, 2, 4, and 5, 7, 6, 8. Anyway, I think I'm going to stop talking about it. This one's not that interesting to talk about. You can read it. So in short, the punchline is worthwhile. What we find in this calculation is that the quaternion 8 group is isomorphic to this particular subgroup of the permutation group, the symmetric group on 8 symbols. So it's kind of interesting, I think. In principle, you could do this calculation for any abstract group you think about, If you have a group of order 14, you could find some subgroup in S14 which is isomorphic to the group just by looking at left multiplication and seeing what cycles back. And all right.
Is there an element of order 4 in... No, there's no element of order 4 in the quaternion 8 group. Oh wait, no.
I, J, and K. Because I to the 4th is 1, J to the 4th is 1. Because I squared is minus 1.
So that's why those all have order 4, and then negative 1 has order 2. And then
Right. Excuse me. What is this? Here we have normal subgroups. And I'm trying to prove something. What was I trying to prove? That the intersection is a normal subgroup once more. So what I do is I pick something in the conjugation of the intersection. My goal is to show that that's again an element of H intersect K. To show that is to show that the conjugation of H intersect K by something in G is a subset of H intersect K, which is to prove, in fact, that it's normal using theorem 9.1 in Galilean. And so that's what I do here. First of all, if X is in there, that means there exists a Y in the intersection such that that's the case. But the fact that Y is in H and the fact that H is normal gives me that there exists an H, well, it tells me that this is an element of H is basically it, all right? And likewise, this is a subset of K because K is normal, which tells me that G, Y, G inverse is an element of K. So it's an element of H, it's an element of K, it's an element of the intersection. Oh no. So, really? Okay. Is Hillary over there? What was that? Oh, so there it is. I mean, that shows that X is an element of the intersection of H and K, which shows that this is a subset of H intersect K, which shows that H is... Of course, if you wanted to, you could prove the left and right cosets are equal, but by golly, I think this is easier. Music, really? What's going on over there? I'm going to go put a stop to it. Let's see here. So suppose the order of G is 36, the order of H is 12, the order of K is 18. And I think when you guys asked me about this, I got it in my brain you had to know something else, but I don't think you actually did. All you needed to know was that H intersect K is a subgroup of both H and K, which I just think is something I wasn't thinking about when I first advised you guys when you asked me questions about it. It just didn't click in me. And that fact is really all I need with Lagrange's theorem to solve this problem, because yeah, exactly. The order of the intersection has to divide the order of H and the order of K, but the only thing that divides both 12 and 18 is either 1, 2, 3, or 6. Yeah, you can't do 4, you can't do 9, because 4 gets 12 but not 18, 9 gets 18 but not 12, 12 gets 12 but not 18, 18 gets 18 but not 12. So then your common divisors. Basically by enumeration of factors and such. I mean, tempting to go over there. All right. This one, what was this one? This basically said to quickly calculate the index, I think it was, of H and D9, and to list the cosets. So, since the order of H is 3, the index of H and D9 is 18 over 3, which is 6, and these are the 6 cosets, right? If you like, and you don't, I mean, I kind of like this, but here's what they are in gory detail, just in case the grader needed to, you know. Oh my goodness. But yeah, these are the same as that. Obviously, this is a more efficient way of communicating. It's not normal because HY is not equal to Y. Wait a minute. Oh, HY is equal to YH, isn't it? And HXY is also equal to XYH because it all goes back to the fact that x minus 3 is x to the 6th. So like, to move this to the other side goes yx to the minus 3. That's the basics of dihedral. If I move an x past a y, it changes n to minus n, is what we should have seen at the end of all of our deliberations. And so to change 3 to minus 3 is to change 3 to 6, because we're working with this. And so likewise, to move, well, I don't have to move that one. That one's already good. But to move, oh, where? I don't know. Curses, I don't know what I'm trying to show you. I guess this one, to move, no. I don't have to move these. Oh, I guess I already did the calculation in my brain. Did I? Oh, maybe I've already got the equalities I need up here, don't I? That's the point. I did it up here already. See, like x, y cubed, yx to the 6th is this, is that. So here I was recasting this non-standard presentation in terms of the standard x first, y second presentation as a means to compare down here. So this, and this support these equalities down here. Oh, man. So, in total, it's normal, and this is a factor group. Let's see here. So this is great and all, but I mean, here I explicitly show the left and right cosets are equal, so it's normal. That's what this argument is, but there's a better argument on the next page, so let's look at that one. See, the question was to show that the identity Cartesian product with H is a normal subgroup of G cross H, if I remember right. Yeah, that's my punchline down here. Here's a better argument. So to see that this is a subgroup, I can identify E cross H with the kernel of pi 1, where pi 1 is this mapping, the projection onto the first thing, projection homomorphism. And the pi 1, if this is equal to E, that implies that X is equal to E and Y is in H, which of course is just to say that the kernel of pi 1 is this. And you can see here that pi 1 is a homomorphism. So the kernel of pi 1 is a subgroup, but you know what? It's more than that. It's a normal subgroup. We've proved that. And so here,
Back to where pi 1 came from.
pi 1 I find right here.
So,
I made it up.
I mean that X, why does it mean that Y is in H? Oh, because X, Y is it?
Yeah, there's no no condition on Y, so Y is just an H. That's it. So that's exactly this space. And so, in fact, I should really be more greedy here. I should put, I should complete it. This argument shows that it's a normal subgroup because we know that kernels are normal subgroups. We've proved that. Excuse me. So one way you can prove something's a normal subgroup is to exhibit it as the kernel of a homomorphism. That's what I did here. To show that the Cartesian product, the direct product of G and H with H and G are isomorphic, no, I won't waste my time. I'm not going to go over there. Let's see, where's there? All right, so basically I just make the obvious isomorphism, which is just old switcheroo, and you can see that that's onto, and you can easily see that it's 1-to-1, so it's a bijection, and then we just have to show it's a homomorphism. I mean, I could have shown it's a homomorphism first, then shown its kernel was the identity to show that it's an injection. But here I just thought, I'll just go back to basic principles and do from the definition for a change. And just to mix it up a bit. So here's the product, but this product is that, right? Direct product you multiply component-wise. Then the definition of the switcheroo map is to switch. We switched them. And then I'm unproducting by the definition of the product in H cross G. Here I use the product of G cross H. And then, of course, that's psi of xy and the switcheroo of AB. So there you go. Psi is bijective homomorphism, and that shows that G cross H is isomorphic to H cross G. Did you guys get that one? I hope so. Pretty much if I put that one on the test, it shows me who's completely lost versus who is like, oh, thank you, Dr. Cook. Please give me another. Let's see here. Let's see here. On to 14, I suppose. Oh, this proof is just, I'm not entirely sure my proof here is optimal or complete, honestly. So when I was trying to figure out how do you prove that there can't be, there has to exist. I mean, it's possible that you have a better argument than what I have here. Well, I get to that eventually. for a later part, but here my argument basically is if it's cyclic, right, then you have an element of order 2, right, a cubed. So that means there exists an element of order 2, woohoo, or it's not cyclic, right? If it's not cyclic, then I think maybe the thing that I should say more clearly is every element has to divide the order of the group. The only possible orders are 1, 2, and 3. Since it's not cyclic, there is no element of order 6. And there's only one element of order 1. So really the question is how the elements of order 2 and 3 are intertwined. Sorry. Every once in a while I use a technical term. Let's see here. Where am I? EAB, G. G is not cyclic. Then there have to be, excuse me, 3 points in G which are not where. Why did I say this? B is not equal to. Why is that? Why? Sorry, I don't. Why did I say this? 3. There have to be. Oh, if it's not cyclic, that means that there are 2 elements that are not the identity, right? And one of them can't be reached to the other by a power. I mean, it says more than that, but that's one thing it says. Anyway, so A is a subgroup, right? So it either has 2 or 3 elements. If the order of A is 2, then A squared equal to 1. So anyway, if the order of the subgroup is 2, great, we got our element of order 2. If the order of A is 3, then you've got E, A squared, B, and then 2 things, X and Y. But since B is also a subgroup of G, it means the order of B is either 2 or 3. So either B is EB or B is EBB squared. Excuse me. If the order of B is 2, great, done. If the order of B is 3, then we've got E. Remember, we're assuming B is not equal to A to the K, so these are disjoint. A squared, B squared. Oh, then I'm back to here. And as Y is not a power of A or B, right, we are forced to see that the order of Y is 2. That's the thing I'm not totally convinced of. Well, I mean, Y can't have order 3. Unless it's...
Because then you have too many elements.
Yeah. Anyway, then that's my best argument at the moment. It might have a gap at the end. Excuse me. There might be a better way to do that. Suppose the order of G is 6 and all elements besides E have order 2. All right. So A not equal to B not equal to E with A squared equal to E, B squared equal to E. Then AB is another element of G with AB squared equal to E. So AB is a subgroup of G, but hey, hold on a second. 4 does not divide 6, so no can do'sville. All right.
Were you assuming that G is the billion?
Let's see here. No, but we're assuming that all elements beside E have order 2.
Oh, so A.
AB is another element. Yeah, it has to have order 2. So, yeah. So if we do have that, then it gives us this subgroup, which is E forbidden.
Wait, why can't you have a third, like another element, X?
But thing is A times B is an element of G. It has to have order 2. So AB squared is E. That means, I mean, you can verify this is a subgroup of G, because the product of any things in here is again in here. A times A is in here, A times B is in here, B times A, let's see here. So you're like, why not B times A?
Why can't you consider A not equal to B, not equal to C, not equal to E?
That's what I'm thinking right now.
A not equal to
But then you'd have too many elements and it still wouldn't
A,
make sense.
what? A not equal to what?
Well, you said consider A not equal to B, not equal to C.
If you
Why
added a
can't you
third element
consider
in
another
there.
element?
I mean, you could, but the point is with these two elements, you can build this subgroup.
Oh, and so you're just going to find a contradiction.
Yeah. I mean, I guess there's a question, which is why is B times A in G, right? Can you tell me that? Why is it that BA is, I mean, I know A squared is in there, B squared is in there. AB squared is equal to E, right? So what is BA then? Well, if AB times AB is equal to E, that says that BA is equal to what? Multiply by A on the one side and by B on the other side. You get A squared, you get B squared. I think I'm outside my camera range. So actually, no, I'm not assuming that the group is abelian, but guess what? Even though I didn't assume that, supposing that AB squared was E forced AB to equal to BA. See that? So the product of A with itself is in the group, the product of B with itself is in the group, the product of A with B is in the group, the product of B with A is in the group. And if you calculate AB times A, you get B. If you calculate AB times B, you get A. All possible products land back to E, A, B, and AB.
Yeah.
So it's a subgroup of order 4, which is impossible. There is a little bit of detail missing in my solution there. Agreed. I would say happily, but I will agree. Not happily though. Oh no. Excuse me. So here, the next part of this so if we have G, a group, and if A has order 3, B has order 2, we're supposed to either show G is cyclic or AB is equal to BA. AB is not equal to BA, right? So, consider G equal to E, A squared, B, and then X and Y, right? I don't know what happens to X and Y is the whole thing, right? Now, if AB is equal to BA, then we can calculate X squared is A squared B squared, which is A squared, and X cubed is ABA squared, which is A cubed B, which is B. X to the 4th is ABBA. X to the 5th is A squared B. X to the 6th is E. Voila, element of order 6, this X is. So, I mean, if AB is an element of order 6. Okay, so not terribly surprising. We have an element of order 2 and an element of order, element of order 2, element of order 3, so it's an element of order 6. Because of that. Anyway, so if it has an element over 6, cyclic. So, done. Yeah. Yeah, this one was actually pleasant. I felt better about myself after working this problem. The last one, I had an uneasy feeling about. So here it is. G group of order 6, so you start writing down the AB not equal to BA case, right? So you've got this AB, and you've also got BA, and so this upper block comes just because A has order 3, and some of these are just immediate, like A times B is AB. We can work out that, let's see here, I don't know where I've got the work. I have more work somewhere. But like I said here, I'm forced to need to put, to not repeat BA here in column 6. Well, in column 6? Oh yeah, column 6. So I've already got AB, BA squared, EA as I was filling this out. And then that forced me to put BA there. And once I put that BA there, looking at this row, it forced me to put the B there. And so that basically starts it. I've got A times AB is equal to BA. And pretty much once you have that, you can generate everything else. You know what I mean? We have, what did I just say? A times AB equals to BA. So we get this A squared B equals to BA. So that's kind of like analogous to the XY equals to YX inverse relation in the dihedral group. This relation, together with the fact that A has order 3 and B has order 2, generates S3. Generates this table, in fact, which then you can see is isomorphic to S3 by just reordering the Cayley table just a little bit. I had to switch I had to switch the column. I think I had my earlier, where I did this before, I had I had to swap something here, but it's pretty easy to see once you start looking at it,
Yeah.
the pattern. So.
When I did it, I put E and then I put A, D, F, because I wasn't thinking to realize that. But then I still was able to work everything out. It was just harder.
Yes. But there you go. That's the isomorphism right there. So that's it. 2 groups of order 6 up to isomorphism, either the cyclic group of order 6 or the symmetric group on 3 symbols. Oh, here's some details. Like I said, we found that is equal to that by necessity of that particular row and column. And that gives me A squared B equal to BA. But if I multiply that by A squared on both sides, that gives me that A squared BA squared is equal to B, and so forth. You can derive all the relations you want from that. I haven't worked with it too much, so I'm not as comfortable with that generator relation presentation of the symmetric group on 3 things as I am with, say, the dihedral group at this point, but there it is. And if you look at group theory books, they tend to start using this presentation of S3 when they want to do calculations. It's faster, obviously, than doing cycles. But it's also a little bit divorced from what this was. Depends on the question, which version of S3 you want to work with. But one of the things we gained from this whole discussion is the fact that we can generate S3 by products of the 1, 2, 3 cycle and the 1, 3 cycle. All right. I think this one wasn't too bad. Suppose we have a normal subgroup 1, a normal subgroup 2. We have the natural homomorphism, the coset map, all right? Natural homomorphism, the coset map. The kernel of pi 1 is n1, the kernel of pi 2 is n2 by construction. So the image is the left cosets of n1, the left cosets of n2 under pi 2. These are the images. So in other words, pi 1 and pi 2 are surjections. We can construct the Cartesian product of pi 1 and pi 2 by the natural rule. That will go from the Cartesian product of g1 and g2, or the external direct product, as we've been calling it, excuse me, to the external direct product of the quotients, according to this rule. And then it's easy to show, well, let's not get carried away. You could show that that's a homomorphism. Here's the proof. I assume we already know that pi 1 and pi 2 are homomorphisms because we worked that out previously. So it wouldn't be much more work to work them out. I'm assuming that from our previous discussion of fundamental homomorphism. So this is that, but then by definition of psi, pi 1 of xa, pi 2 of yb, but these are homomorphisms, so pi 1 of x, pi 1 of a, pi 2 of y, pi 2 of b, which, by the way, unproducting is pi 1, pi 2 of x and y, pi 1, pi 2 of a and b, respective, which, of course, is the homomorphism property. So we have that psi is a homomorphism. Any question? No? And so what's the kernel? Well, the kernel is exactly it works out to being the Cartesian product of the kernels of the maps which we're producting. And so it's just n1 cross n2. So then the first isomorphism theorem says that if we look at g1 cross g2 mod n1 cross n2, that's the kernel. So it's going to be isomorphic to the image. By the way, the image is the quotient cross the quotient, because that's pretty clear that these are surjections onto that and that. So the image of psi is just this cross that. I don't know if I prove that explicitly here. Oh, no. I guess I have not. I'm just claiming that. I suppose I haven't actually shown it, but I think it's clear. You should show those sorts of things. Yes, okay. Now, how did you do this problem? Or you just were like, I don't know what to do with this problem?
I sort of tried to follow that example.
If you tried to attack it directly, it would be kind of intimidating. Yeah. So there it is. That one. I don't think I have 15 scanned in here, but I just scanned some more. Let me look it up here for a second. Let me see. Uh-oh. Huh, well. Where'd I go? Here it is. I wanted to see if his question was something like short and that I could do here, but it's not, so it's cool. I have not posted these yet, but I will, despite the fact that they're not. I'll post this scan if I remember after our meeting, but it's got from a couple different lectures. It's a work in progress. It's not quite done. Some of it's done though. It's like, here's a fixed version of the horrible problem that wasted our time. So if we have a surjective homomorphism from Zn to Zk, surjective, then it is in fact true that K must divide N. Why? First isomorphism theorem says that Zn mod the kernel of phi is isomorphic to Zk, because it's generally you have to put the image of phi here. So if it's surjective, that's the image. So the order of Zn is n, the order of Zk is k, so you get also, by the way, the order of the quotient is the order of the group divided by the order of the subgroup. And so what do we got? N over kernel phi order is equal to k, which is say n is equal to k times kernel phi, which is to say k divides n. So it is true in the case that it's a surjection. But my counterexample in the announcement was, if you look at phi of x equal to 2x from z4 to z6, it's not a surjection, and it also doesn't have, 6 doesn't divide 4, and yet it's a homomorphism. Yeah. So anyway, my apologies. This one was fine though. Although it may have gotten collateral damage from the confusion in 57, unfortunately. So here we define psi to be the coset of x, just switching the moduli from n to m. And since I want a surjection, right, I'm going to need that m divides n, right? I know that from the fixed up version of the last problem. Okay, so I need the condition n divides m. But anyway, I'm gonna assume, I'm not gonna assume that makes it work. I'll actually show that it makes it work. So assume m divides n. Let's show that psi is well defined. So look at two different representatives of the same coset. That means x prime is equal to x plus nk. And so psi of x prime would be psi of x plus nk in the m, mod m. But remember, n is equal to m times l because n because m divides n. So n is a multiple of m, and then of course this is 0 because it's m times stuff, which gives you x, which goes to show you that psi of x prime is equal to psi of xn, which is to say that psi is well defined. So it's a function. Woohoo! It's also clearly into because its output is an m it's an equivalence class mod m. So like the into is there's nothing to check into wise here. Sometimes there is, right? But not this time. And so it's a function, and it's a homomorphism too because we've got this plus this is that plus that, which then by definition is the m coset, but by properties of equivalence classes mod m, that's equal to this, and then but that's exactly that plus that, so homomorphism. Woohoo! The kernel is just the set of n cosets of x which have m cosets mapping to 0, but that's exactly when we have x is equal to mk, right? So put that back over here, and you get kernel of phi is mk n, which is of course just the m multiples of zn. Yep.
So when did a bracket around x?
That's a notation for the, I'm going to get this eventually. So that would be brackets x n is equal to x plus nz. It's the coset of n tuples. I mean, it's basically the set which, more explicitly, it's x plus n, x plus 2, well, plus or minus n, plus or minus 2n, and so forth and so on. And we can add those sets of integers that reproduces what we call modular arithmetic. Now, a lot of times I'll just use x rather than x with brackets n. The reason I'm using x with brackets n here is because the whole point of the problem is about bridging the world between mod m and mod n. So if I use a less explicit notation, it makes the problem impossible to understand. Like if I just use x without the n adorning it, the mapping would just look like psi of x equals to x, and we would lose,
So it's the set of x mod n, basically?
Yeah.
Okay.
It's the equivalence class of x mod n. It's really x, quote unquote, in Zn in our usual notation, but our usual notation won't work here because we're working with both mod n and mod m. So we need something more explicit. I used this kind of notation back when we were building properties of modular arithmetic. It's just once we get past that, we're just working, we don't like to use this notation because it's, if you look at some books like Beachy and Blair, they continue suffering the brackets even past the point where they're convenient. But whatever. Anyway, then first isomorphism theorem, that's the kernel of a homomorphism. So the domain mod the kernel is isomorphic to the range, and the range, the image here is of course the whole thing because this is clearly a surjection, right? You pick any, you pick your favorite thing in Zm, say x, then psi of x mod n map to it. Oh, this one I like. Whew. All right. So first of all, you notice that cosine and sine are never both 0, which means that it maps into the non-zero complex numbers. It remains to show it's a homomorphism, but that's just adding angles formulas for cosine and sine, and then multiplying. So if you multiply this out, you get back up to here, which is to say that that's a homomorphism. And then the image, well, this is a homomorphism. The image of a homomorphism is a subgroup. But the image of this homomorphism is also the circle. So that proves that the circle is a subgroup of the non-zero complex numbers under multiplication. That is all. Now, of course, you guys probably didn't do it that way. You probably proved that the circle was a subgroup by like direct calculation or something, right? And that's fine. But if you look at what you did, the calculations are actually the same as these. Yeah. So, you know, there's more than one way to skin a cat, but in the end, the result is what it should be. This, well, I'm not sure I entirely believe this solution yet. I mean, I shouldn't talk about this because I have doubts, and I'll just exasperate the doubts, and it's a solution, you can look at it. Yes, ultimately that one comes down to counting. Okay, so normal subgroups, we're supposed to prove the product is normal. So what I do is I start by proving a pair of normal subgroups product is normal. So here's the proof of that. If I pick 2 points, A and B, in the H1, H2, then that means they can be written as A1 times A2 and B1 times B2 by definition of the product of H1 and H2. But since H2 is a normal subgroup of G, we also know that B1 inverse H2 is equal to H2 B1 inverse. So that means that there exists, notice that this is an H2, right? So that means that A2 B2 inverse times B1 inverse is an element of that right coset. Which means, incidentally, it's an element of this left coset. Right? Which means there exists an H2 such that A2 B2 inverse B1 inverse is equal to B1 inverse times H2. I'll use that momentarily. So if I look at AB inverse, I've got that. Now this is happening inside a group, so I know I have Sock-Shoes formula for that. That's just inside the big group where else is happening, G. But the issue is, can I show that this is in the product of H1 and H2, all right? So that's giving me B2 inverse B1 inverse. And now you see why it was I was picking on A2 B2 inverse B1 inverse. It's because I wanted to move this B1 inverse over there. So I move it over there, and now I've got A1 B1 inverse H2. But check it out. That's something in H1 times something in H2. Consequently, AB inverse is in the product of H1 and H2, which is to say that H1, H2 is, I would say that we can conclude H1, H2 is a subgroup by the one-step subgroup test, but we don't yet know that H1, H2 is not empty. So to see that it's not empty, I notice that the identity is in both H1 and H2 because H1 and H2 are subgroups. And of course, EE is equal to E, which means that E is in H1, H2, which is not empty. And so at this point, I know that H1, H2 is a subgroup, but I have not shown it's normal yet, right? So to see that it's normal, oh, stop that. So if I consider, Z in the conjugate of H1 and H2 by G and G, that means that there's some x1 and x2 and h1 and h2 respective, like this, right? But we also know that this and that are equal, and that are equal, because h1 and h2 are normal, so their left and right cosets match. So that means that there exists an x prime and an x2 prime such that gx1 is equal to x1 prime g, and x2 g inverse is equal to g inverse x2 prime. So when I look at z, I've got gx1, x2, but I can rewrite that as x1 g inverse x1 prime g plus g times g inverse x2 prime, the g and the g inverse, poof. And then we've got x1 prime, x2 prime, which of course is an element of h1, h2, which is to show that the conjugate of the subgroup is once more a subset of the subgroup, which is to prove that it's normal since G was arbitrary. So then we have that the product of two normal subgroups is once more normal than G. And so what? So that's 2. What comes next? N. Yeah, I did 3 just to be cute. But, you could have jumped N just the same. It's pretty much what, if you look at this, my argument for 3 and my argument for N, they're the same argument. Look, to get 3, what I do is I go, aha, H1 and H2, I already know is a normal subgroup. So I can look at this as like H prime times H3. But H prime is a normal subgroup, so we can apply our argument for 2 subgroups to get that H prime H is a normal subgroup of G. Thus, H1, H2, H3 is a normal subgroup of G, and then you can continue in this fashion until we obtain that to be more, proper. You could do it in an induction. If you assume this is a normal subgroup, then if you look at the n plus 1th product, well, we already know that's a normal subgroup, and that's a normal subgroup by assumption. So by the n equals 2 case, the product is again normal. So it's always the 2 thing. Just I feel like this is not a real induction in some sense. I don't know. That's just me, but we're not doing this for all n. We're just doing it for all n less than or equal to k minus 1. Since I do n plus 1, n plus 1. n plus 1 ceases to have meaning if n is more than k minus 1 in my context here. But anyway, there's that. Oh, this one's fun. This one wasn't bad at all.
I actually had to leave.
Oh, okay. Well, anyway. So there's this one. Anyway, I have this one worked out in gory detail. And this one, you guys probably got this one, right? I bet you guys got that one. The order 15. And I also have this one worked out. And I've got the characteristic group one worked out. This one I'm still working on. Not that I'm lost, I just don't have it done yet. And then number 54. So I got a few more that I'll post, but anyway. And here's part A in this one. But anyway, shut up.
All right, thank you.
Yeah. It's probably better that I'm stopping now anyway. So I'm starting to cough more and more.
See you, Mark.
Yeah, we'll see if I do anything productive tomorrow. It remains to be seen.